Welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. Today we have the pleasure of having Jean-Michel Loubes. He's Professor of Mathematics at the Institute of Mathematics of Toulouse. He holds the chair on Fair and Robust Learning at the Artificial and Natural Intelligence Toulouse Institute. He has other projects around anomaly detection in machine learning, applications of optimal transport in machine learning, and machine learning in human evolution and medicine. He has published in journals such as the Annals of Probability, BMC in Bioinformatics, Journal of Multivariate Analysis, and the Proceedings for the very prestigious conference, the International Conference on Machine Learning. He is Associate Editor of the European Journal of Statistics and member of the Scientific Committee of the CNRS Mathematical Institute. So we are very, very pleased today of having Jean-Michel. The floor is yours. We will have the Q&A session at the end, but if there is a very, very urgent question, the audience can post it on the chat and I will read it for you so that you don't need to be checking the chat. Thank you so much.
Thank you, Dolores. It's a pleasure for me to present today. So if there are questions, please interrupt me and tell me, because I'm making the full screen share, and unfortunately I do not see anymore the chat, so it's completely blank for me. So today I'm going to present some recent work dealing with fairness or bias in intelligence, in artificial intelligence, and especially in machine learning. So first, I just want to define what is bias. So it's very complicated. So if you look in the dictionary, you see that what is meant by bias is that it's about some irrelevant information that influence a decision but should not. So it's closely related to the notion of unfairness or confounding effect, and we're going to see that how does this notion interacts with machine learning. So I'm going quickly to recall the principles of machine learning that are at state when you study bias. So it has everything to do in machine learning how a machine sees the world. Indeed, I'm going to put myself in the framework of supervised learning, where you look at a variable which is called x. I don't know if you see when I move my pointer. I'm afraid you're not. Okay, so I think you don't see when I move the pointer. Do you?
So you are sharing your screen?
Yes.
Or sharing your.
Okay. So I'm going to do otherwise. So when in a supervised setting, when you monitor a variable x, which could be multidimensional, and you want to be able to build a model that will going to forecast a new variable y. So in fact, when you give a machine the power to build a model, the machine is only looking at the way the data were generated. In fact, they look at the unknown distribution P of the couples of variables, the target and the variables, yi, xi. And in fact, they do not know this distribution, but they just have access to the observation which follow the empirical distribution that is called Pn. So the aim of machine learning is to be able to design a model, I mean a function f that will be taken into a collection of models that we call capital F that minimize a criterion in mean. And what is the criterion? The criterion is just a way to measure how close a forecast y hat is from the observation L. So you define L, the loss, which is 0 if y is equal to y height in the sense given by L. So if you knew the way the data were generated, you will build what is called the oracle. That means the f function f star, which minimizes the loss for all the possible way of generating the data. In fact, you don't see that, but you have only access to the empirical distribution. So you build the model, the algorithm by machine learning, by just minimizing over the set of all models the function that minimize the loss function. And sometimes to prevent overfitting, you don't want only to minimize the loss, but you maybe want to add a penalty controlled by a parameter, lambda, that is a way to measure a trade-off between the complexity of the model or the smoothness of the function and the closeness to the observation. So you have built this model, and you are very confident that you can use your new model to forecast new observation. And you're very confident. Why? Because, in fact, you have lots of theoretical results that show that the best way you could do, in the sense that you can control the generalization error, you control what is called the excess risk, which is the difference between the loss of your model that you learned f hat and the best way you had to construct a model that is the oracle. So the excess risk, this is the difference between the two errors, is you can prove that for well-chosen model or well-chosen penalty that this is small. But so in fact it's working very well, and now machine learning models are very popular, and you can use them. You can find them used a lot of time in the everyday life. But so what could possibly go wrong? Because maths are objective, you minimize the criterion, so everything should be all right. In fact, since science fiction movies or books knew that artificial intelligence or this kind of model could not be trusted, and they had this intuition, and you can just check, for instance, that there are some decisions taken by the machine, despite all the technological and mathematical correctness, that do not give you the result you are waiting for. So, for instance, if you look at natural language processing, you can make the experiment by clicking on the link. You can do it by yourself. You take a sentence, and the sentence is: a doctor ran to the emergency room to see, and here you put a mask. That means you hide the right word, and you use a machine learning model to forecast what should be the pronoun. And you see that the machine at 38% is predicting that the correct pronoun should be is. At 36.9% it should be the, and you see only at 6% it should be a. So what does it mean? It means that you have built a model which is sexist, in the sense that the machine has learned that the doctor could be a man, but it's very unlikely that the doctor is a woman, since in English pronoun have gender, and her patient would mean that the doctor was a female. So it means that you have gender bias. It means that when you forecast, you use a variable, here the gender, which we call a sensitive variable, to make a forecast. Sometimes And this is a common type of bias that you have in machine learning. Sometimes you have a different type of bias. That means that sometimes the bias is not only in the forecast, but the bias makes that the algorithm does not work in the same way for different subgroup of population. So here I take an example of image analysis used by Amazon, and you see that the algorithm works very well for a Caucasian male. If you were non-Caucasian but still male, then you degrade it by 1.3%, which is quite small, the accuracy of the algorithm. But if you are a female, then you lose almost 7%, which is huge if you look at the level of accuracy of this type of algorithm. And it's even worse if you are in the true minority class. That means if you are an Afro-American female, then you see the algorithm is not working anymore because the accuracy falls to 68%. This is a kind of bias which is in sociology called intersectional effect. That means that when the bias is not the simple addition of bias, but joint bias is worse than the sum of all bias. So how is this thing possible? It's possible because when you do machine learning, you optimize your criterion, just minimize your loss function of a collection of model. But what do? We all want to do that because what we want in the end, we hope that the algorithm we find will be a good model in the sense that it will be relevant as a good way to understand the information conveyed by the observation. So you're going to minimize and you find something which is sound and which is relevant what you're looking at. And that's why you're very confident to use this. But maybe you're not doing that at all, but you're just trying in a huge data set, you're just looking at correlation between the data, X, and a variable. So you look, when you minimize, you just focus and just you use correlation. And sometimes correlation are bad. And here you see that you have correlation with respect to gender, but then you transform a correlation into a causal decision. And sometimes the situation could be even worse. Maybe you just learn that a new variable, a new individual, is very similar to an individual you had in the database, and you're going to forecast as if this individual was the previous one in the database. So everyone knows that correlation bias are everywhere in the world. That's at the basis of a machine learning algorithm. But when you try to transform the observation into a model, then you may amplify bias because, in fact, you want the model to be used in our world by looking only at the image of the world through the data. So when you do that, you have a large chance to amplify some bias and to translate this into what I call the algorithm world. And even if you were very cautious and trying to have a data world very similar to our world, maybe our world is not the world where we want to live. We want to live in a better world. For instance, if I am in France and I want to use a machine learning model to forecast if someone could be higher, for instance, as a data scientist, then I'm pretty sure, if I'm not cautious, if I use the data as they are recorded, I'm going to have a gender issue, and I will have at the end an algorithm that will amplify the bias already present. So maybe the world you want to create should not be driven by our world, but by an ideal world where there will be no bias. So you see, bias and unfairness is a very difficult issue to deal with. So just another example, which is a very famous example based on a variable data set, which is an adult data set. It's from the UC database. Just to show you how this issue of bias works. So, for instance, in this standard data, your aim is to forecast if a loan can be given. So to minimize the risk, banks want to be able to predict if someone is going as the possibility of having what is called a high salary, and high salary is greater than $50 kilo. So for that, you have lots of variables. So you have the age, working class, education number, and lots of variables. And among them, you have the sex variable. So if you look at the data, if you look very quickly, you see that the data is not balanced. That means that if you look at the proportion in green of female which have a high salary, it's a lot smaller than the proportion of male with high salary. So you may have the intuition that if you're going to learn why someone has a possibility of having a high salary, then it should be susceptible to be biased with respect to this variable. So if I use machine learning algorithms, I'm going to use 3 algorithms, which are one very simple, which is a logistic regression, which is a linear model, everything standard. Another one, I'm going to use a classification tree, and then I'm going to use a black box model, which is a extreme gradient boosting. So you see that if you look at the accuracy figure, you see that I'm going to predict quite well. I have around 85% of good prediction. But what I can look at some measure of bias. I can look at what I called DA, which means disparate impact, which is a standard measure to measure how bias affect in decision. And I can measure the proportion of people who have a high salary, that means that have Y equal to 1, among group of women, so among the people who have A equal to 0, so gender is modeled by the variable A, which is 0 if it's a female and 1 if it's a male. And I can look at the proportion of female with high salary divided by the proportion of male with high salary. So if the variable was not playing any role, this proportion should be equal to 1. If this proportion, if the disparate impact is small, then it means that the probability for male of having high salary is a lot greater than the proportion of female. So you see that in the data set, there is a level of unbalancedness which is around 0.37. And then if I replace Y by the proportion predict, that means by Y high, predicted by the logistic regression, the tree, or the extreme gradient boosting, you see that I do not correct bias, but it's even worse, I amplify the bias. That means that my 3 algorithms are even more unfair than the unfairness of the usual situation. So you see that it's really an issue that I should correct. And there, you know that there are the GDPR and the European Act on Artificial Intelligence. And what do they say? That say that maybe the solution should be not to use the variable. So let's do this, and let's remove the variable from the database. So I remove the variables, and then I run again my algorithm. So I remove, and you see that it's completely unchanged. If you know statistics as mathematician, we are not surprised, because we already know that it's all has to do with correlation, and in fact, the gender effect is not directly on the variable, but it's due to all the correlation with all other variables. So if you remove only the variable sex and not use it, then you change nothing. So you hide the variable, but you still have something which exhibits a very biased behavior. And it's even worse, because if you are, for instance, you are a lawyer and you want to test if the algorithm. So what you will do what is called a testing procedure. So what is a testing procedure? It's something which has been used for decades. In fact, the first proof of testing to detect discrimination is for 1939. You see, so what you do, you create a fake individual which has exactly the same characteristic, and then you just swap the the sensitive variable. So you take the data from women, and then you just say that this woman, in fact, is a man, and you test the difference. But if I'm a data scientist, maybe I want to build a model that is resilient to this change. So what do? I just going to build an algorithm to optimize my machine learning setting, and then the algorithm will be the decision I take will be the best decision, the most favorable decision, whether it's a man or it's a woman. So that's what I call best. I have the best SV. So you see, if you look at the right figure, that the accuracy are just a little smaller, that it's very, I just was very little and sometimes almost nothing. But if you look at the way the bias is changed, you see that the bias is not changed. So again, as a statistician or as a mathematician, you knew already the answer without looking at the figure, because you already knew that the variable A does not play any role. You can remove it, put it. If you do not change the variables, then the algorithm is going to know beforehand, before looking at the variable 8, whether it's a man or it's a woman. And there is the notion I'm looking at is a notion of group bias, and of course it's not changed if I just look at such little change. And of course, due to the new regulation, this is highly punishable by law. So now it's time to define a little more, in a more mathematical way, what is fair in machine learning. So first, sorry to disappoint you, because in fact there is no consensus for a single definition of fairness. So we say that an algorithm is unfair if you're able to define a variable which is called a sensitive attribute, and you detect that the outcome of an algorithm is biased, so is change is affected by the variation of this variable, why it should not. So if it should not, for a legal issue, in the European Act, you have a list of characteristics that should not affect a decision in a high-risk system, or because it's not moral, it's not ethic, or because if it's not moral bias, because from a technical point of view, you do not want to use this variable. So again, if I come back at my two-class decision model, where y is either 0 and 1 for failure and 1 for success, my variable a is 0 or 1, then if I look at what I call the disparate impact, it's a measure of fairness, and the closer to 1, the more fair it is. That's described what is called the statistical parity, which corresponds to the first example I show you. So that means that the variable should not play any role in the decision. And the second case was about performance. So the second type of bias, which corresponds to the second example, deals with what is called equality of performance, where you look at the probability of being mistaken. That means that you forecast y equal to 1, while y should be equal to 0, or you forecast y equal to 0 while y is equal to 1, and you look at the difference of the two probability for the two groups, whether a equal to 0 or a equal to 1. So if y equal to 1 is a success, then you could look at the probability of forecasting a success while you should forecast a failure, or the other one. And sometimes, of course, if you grant a loan, you're not able, for instance, to look at both effects, because if you don't grant a loan, then you're not able to see what would have happened if you had granted a loan, and this should be dealt with what is called counterfactual model. So when you use an algorithm to shape the reality, then you are just able to control one term of the error and not the other one. So fairness, in fact, besides this measure, in fact, has everything to do with the notion of independence of distribution. So full fairness, the real fairness, say that you have these two ways of defining the fairness, or the algorithm should not take the variables into account while forecasting. That means y should be completely independent from a, or the other one, if you deal with equality of performance, then y hat should be independent with respect to the variable, the sensitive variable, conditionally to what you observe. I mean, conditionality to y. So if y hat is a binary and you prefer a continuous variable, you can replace y height by a score, a probability of success. If you're looking at deep neural network, you can look at the score at the n-1 layer just before doing the ReLU attribution. So the idea now is that you have clearly this notion of fairness defined as independence in distribution. So you want to achieve fairness. So why not achieve fairness? And a simpler way to achieve fairness should be to project all your classifier into the fair model. So you pick one fair model. So for instance, I'm going to talk about fairness with respect to statistical parity, and I'm looking at f statistical parity. That means that all the function fxa such that y hat, which is equal to fxa, is independent from a. So in this case, rather than minimizing over the set of function, I want to be able to restrict to the set of function where I have this notion of independence. So this is very abstract formulation, and the idea is first to see if this is feasible and what is the price what is my price to achieve this fairness. So the price for fairness should be the accuracy of the model, that means the risk, the minimal risk for overall fair model, minus the risk, the minimal risk I could do for all the best of both. So you all know that, for instance, if when I want to minimize, then the best estimator is what's is called the bias estimator, which is the projection, in fact, of y given x if I am in a regression setup, or the probability of y equal to 1 given x if I am in a two-class classification. So what changed here? What changed that normally you have one bias estimator, but here, if I condition my bias estimator with respect to the sensitive variable, then in fact I have two best way of classifying my data, and I can define eta a of x, the bias estimator for the class a equal to a. So if I'm looking at a binary class 0 or 1, I have eta 0 and eta 1, and I will call mu 0 and mu 1 the distribution of this bias estimate. So what I want to do, I want to look at the minimum risk. So if I write my minimum risk in the, so I'm going to look at the regression case. I'm looking at the regression case, and then I can look at the error. And if I just condition my error, which is the expectancy of the square of the error, then you see that if I call gx of a any model, then if nu a of g is a distribution with respect to x of my regression function given a equal to a. So in fact, the idea should be to see if this maybe okay. Just a question. Do you see my my slides still?
Yes.
Yeah.
Okay, and now you see the pointer.
Yeah.
We do.
Okay, perfect. So if you look at this expression, then you see that in fact I'm looking at the expectancy of a variable which has with distribution nu a and a distribution of a variable which is the bias estimate. So this quantity is the expectancy of between two distributions, the one given by the bias estimator and the one given by this one. So to go further, I need to introduce a way of measuring the distance between the two probabilities. And that's exactly what it's achieved by optimal transport distance, which is called the Wasserstein distance. So what is the Wasserstein distance? If I take one distribution mu and another distribution nu, then the Wasserstein distance between mu and nu is the minimal coupling between any distribution which has marginal p and nu. So I minimize over all the set of couplings between mu and nu with marginal mu and nu, the distance between one marginal with respect to another one. And in fact, if I look at my quantity here, so this quantity is a coupling between a variable with distribution nu a of g and another one which has distribution mu of a. So this function is a coupling, so it's greater than the minimal way to move mu a of j to mu a. So if you understand this thing, then you understand everything in the proof, because if I come back here, I can use a kind of Pythagoras argument, and then I can prove that, in fact, the price for fairness, that means the fair risk minus the bias risk, is greater than the integral with respect to A of the Wasserstein distance between mu A. So mu A, again, is the conditional distribution of the bias estimator given A, and mu A of G is a distribution of the classifier I choose, the regression function I choose, given A. So now, if I want to enforce fairness, that means if I want to choose G, which is fair, in the sense that mu A does not depend on A, then my price for fairness becomes an equality, and here is the excess of risk is just the infimum over all G which have distribution that minimize this criterion. So mu J here does not depend on A to enforce statistical parity. So in fact, if I look at that, then you see mu A is a distribution of the bias estimator for each subgroup. So if I come back to my gender case where I have two groups, so I have one mu 0 and one mu 1, then I'm looking at something which is in between with respect to the Wasserstein distance. So I'm trying to minimize the Wasserstein distance between any function mu G, here distribution, with respect to mu 0 and mu 1. And in fact, this formulation corresponds to what is called the Wasserstein barycenter. So when I try to minimize this condition, then if A is discrete, this this expectancy is just this sum. And you see, so I'm looking at a regression function G whose distribution nu is minimizing this quantity, and this is exactly the formulation of what is called Wasserstein barycenter. So Wasserstein barycenter is something which was invented by Agé and Carlier in 2015. They gave a mission to ensure the existence and uniqueness of this barycenter, and now I can provide a feasible way to construct my best fair regressor. So I just, for sake of clarity, I just take the case where I have a one-dimensional regression. So if I have a one-dimensional regression, what change? It changed that I can write the transport. So if I have T lower s is something that push mu s towards the barycenter, and T upper bound T is something that push the barycenter towards the other one. So the idea is the following. What do? I compute all the bias classifier, eta sx, and I'm going to combine to use the linear combination of all the barycenter that I push, that I push towards this barycenter. Just to clarify, just show you the feasible way to construct. Then if I have two classes, I compute the bias estimator for the women. I build the bias estimate for the men, and then I take any function which is here, and this line here, this the green are just the barycenter, the Wasserstein barycenter of this distribution. So here we have a feasible way to achieve this cost of fairness, and this cost of fairness is just the way finally to replace something that should be two models or any model as A as values by a single model. So you can also understand this as a way to post-process. In fact, you have here, I put to achieve optimality, I put here the bias estimator, but in fact, if I had any machine learning algorithm, then I could have a model for men, a model for women, and if I look at the optimal transport between the scores and I push them into the barycenter. And this is a way to ensure that my estimator, the way I construct, is optimal in the sense that it matches the lower bound of the model. I presented this work about regression. In fact, it's completely the same in regression, and in this paper you have the exactly generalization of what I presented to classification. The question now is, what do I have achieved? In fact, I have just shown you that if I want to be completely fair, then I can do, because I can project. But I just show you that it comes at a cost. It's a loss of accuracy, and I have a way to control this loss of accuracy. I can quantify using the Wasserstein distance between the distribution of the distribution of the fair classifier with respect to the classifier of each distinct module. So I can really quantify this price for fairness. The main question is it really what I want? Is it really what I want? Because if I use accuracy to choose the model, then I assume that the way I measure the accuracy of the model is a good way. But if I suspect that my world where I take the data is biased, then accuracy is not biased. For instance, if I minimize accuracy for the existing data, then I will just perpetuate the bias, the present in the data, and then I will just assume that I want a kind of status quo. I mean that I accept the bias in the data, and what I just want to control that the algorithm does not make the bias worse, does not amplify the bias. The question is also, maybe accuracy is very important for me, and the price to pay is too much. So in this case, if the price to pay is too much, then I want to just mitigate bias, and I want to replace my condition of independence. So I want to weaken the notion of independence. And here, unfortunately, there is no consensus, because to weaken independence is very clear, but to weaken independence is not clear. You have to choose a way to measure this independence using a correlation, using Renyi correlation. You can look at the rank. You can look at the famous H-seq, which is the inverse Mick criterion. And then the way to do it here, to add a fairness measure to the way you minimize the data. So I want to show you some example of what you can do in practice using a model, which is a regression in econometry. So assume you are in the famous example in econometry where you want to select students based on some score. But you measure the score, and the score is a way to express the capability, the intelligence of the students, but the score is biased because depending, for instance, on the school the students were, then the school prepare them. Some school prepare better for the final exam rather than other school. So you have a regression, and you want to decorrelate the effect of the school, and the way they do in econometric is to use what is called instrumental variables. That means that the expectancy of the noise given x is not equal to 0, but in fact, if you use the instrument, then here you decorrelate. The issue is when you write this expectancy, then the equation becomes, in fact, an inverse problem. So instead of looking at y, a standard regression model, your model becomes this inverse problem, k phi is equal to r. And k is the integral operator, and r is just the expectancy of the observation given w. So if you want to add fairness constraint, then you want to look at several constraints that can be used on phi in order to remove the effects of some sensitive variable. So to do that, you just, so that's standard results in non-parametric regression. And the way to do that without fairness is just to use Tikhonov regularization method, and then there are lots of results that give you rates of consistency of such algorithms. So if you want to do fairness, then you will say that x is equal to z of s. S is the sensitive variable, and you want to remove this S effect. So you want to look at what should be the good forecast if it was independent from S. So if you look at a linear model, then you can write the statistical parity constraint like that. And in fact, you can see that the constraint is a kind of image by a linear operator of the function. So in fact, the fairness constraint here, the independency, you can write it as the fact that the function belongs to a kernel of some operator. So here in this specific case, you can see fairness as the fact that phi belongs to the null space of a linear operator. So now the projection to fairness becomes something that you can write from analysis point of view. You have phi, and phi you have an image to R by a linear operator. And the question is, do you want to solve your functional equation and then project to fairness, or that's one way to do that, or the other way around should be, I don't want to solve my my equation and then project, but I want to solve my equation by constraining my function to belongs to the null space. So here you have finally two ways of ensuring fairness. Both functions are fair, but the issue is that the two are different. So what do you do in practice? In practice, basically you say, okay, I'm going to impose the fact that phi belongs to the kernel. So the natural way to do that is to add a fairness penalty, and you want that this trade-off to be large enough such that this term is very small. So what you can see that in fact, if you do like that, you will converge. You will not converge to this solution, that means the solution and then where you project, but the solution where you have solved the equation directly in the kernel of the operator. So you see that if rho goes to infinity, if this is large, then you recover the Tikhonov rate of consistence. So here you have a way to ensure a way to construct the fair regression in this context. But what is the price for fairness? And here I don't have the real answer, because the only thing I can show you is that in fact the price for fairness should be how my estimator will deviate from the standard estimator. So what I can prove that my fair estimator deviates from the unfair solution by these parameters. And you see that this, then the bound is in rho divided by alpha square. That means that rho, I just recall, was the parameter I used to ensure fairness. So when I was looking at the consistency towards the fair function, I would want rho to be very large, but the larger I want, then the more I deviate from my original solution, which is quite normal because my original solution is not fair. So if I look at some simulation, I can see that in fact rho can be chosen with respect to the regularity parameter, and then in fact I can find a minimal value such that I'm close to the fair solution but not deviate too much from my usual solution. So just to conclude, I have tried to prove you that fairness is important, and that if you really want to be fair, then you can do that. You can do that by really removing the effect of the variable. I've shown the statistical parity. So you can achieve fairness, but then you can quantify what does it mean to the estimation. But what should you do? And that's maybe the real question. Do you really want to do maths and just try to minimize a trade-off between the accuracy or the change from the unfair solution and the level of fairness you ensure? Or do you want to forget completely about accuracy and pay the price for fairness just to be fair? And in fact, I have no solution to this one. There could be another solution. I could have a solution from an economic point of view if I could add the price I get for being fair. And in this case, I could remove my accuracy by a gain for fairness. But in fact, if I just use accuracy, then I don't know if I want to pay the price for fairness of not. And just to conclude, being fair from a machine learning point of view does not mean I'm fair by a moral point of view. So I've seen a lot of applications which were completely unfair by design. For instance, I've seen applications where people wanted to forecast if children age 6 were going to commit crimes when they're grown up. And even if you put fairness penalty, I'm quite convinced, so this kind of application is completely unfair by design, even if you try to put any fairness penalty you could design. So thank you very much. I'm going to stop here. And if you're more interested in the topic, you can look at the biography, and in bold you have the paper from which I took the mathematical result I present today. Thank you very much for your attention.
Thank you very much, Jean-Michel, for this very interesting presentation on a very timely topic. Is there any question from the audience? If so, we will unmute you and give you the right to share your screen. So we have a question from Emmanuel. So Yasone, if you could please the rights to Emmanuel.
Hello, thank you for your very interesting and, as Dolores already said, very timely presentation, very clear for me. So my question is more on the technical side regarding the last model you showed us, this regression model or econometric model, where you basically address the question, what happens if you exchange the order of projection, right? Somehow you do.
Yes.
You don't.
So
and you said it depends on. I think there's a well-established literature about this topic also regarding convergence results. About the and your picture is also very well capturing the decisive quantities here, namely the angle between the two subspaces. This angle is responsible for the for the speed you could converge in repeating these iterations, because then you can first project on the fairness, then go to the closest point there, and go back, and then and so forth. So I wonder how this could be operated in your estimates or in your precision here. And the next question then, of course, is we are always looking at criteria in machine learning, as you nicely explained. Actually, and you addressed it shortly, so I wonder how would I proceed in practice? Would I really care if I'm far away from the unfair solution criterion-wise? Because even the criteria, even the least squares fit or something is not really important in some context, and the less importance is the, how should I say, the configuration of the parameters in the parameter space. So probably I don't even care how far I am from the unfair solution, the fair solution. Can you please explain also the role of the criteria as opposed to the role of the distance in the parameter space? Thank you.
Okay, thank you for your very interesting question. So in fact, to solve the problem here, I just present a first paper that we just finished with Samuele Santorino and Jean-Pierre Florence, and in fact, we used Tikhonov regularization. So that's why you can look. I do not run, but every time I put the assumption, you see beta smaller than 2, which has nothing to do with the true regularity, but it's really driven by the choice of a Tikhonov regularization. So so in this case, the way we model fairness is through an operator, to be anyway, and we say, okay, my fairness is in the null space of this operator, and then in the Tikhonov case, then we have this, the way we write it, and this enforces us as looking at the function which corresponds to this solution, because when rho increase, then the rho effect is greater than the regularization. So we first, in fact, it plays as if we first enforce fairness and then solve the regularization issue. In the second in the second part of work we're doing, we try to look at other kinds of regularization, and the one you suggest is exactly the kind of iteration where we solve it like it's a kind of Landweber iteration where each time we enforce smoothness and we enforce also fairness at the same times. My intuition is that we're going to recover the first one. No, sorry, the second one. My intuition is that we're going still to recover this one because, in fact, in this one we have no control because fairness. If I look at the equation, when I want to enforce fairness in the solution, then I'm quite pleased that, in fact, the fairness is related to the way K acts on the function. So it's fairness. The fair solution depends on K. And I think it's quite natural. And I think the first way of looking at fairness, it's not natural at all. And rather, this one is sharp. So that's, but in fact, the thing you say that look at fairness, then approximate, then come back, project, and that's exactly what Landweber. It's another way to do that, and that will enable us to have better Hilbert scales than the one of Tikhonov. The second criterion, I don't know. In fact. My main issue, and it's not related to this one, is that in this case, I don't know what is better. If it's better to be close to the first solution and being fair, or if it's being fair and being not close to the operator. And that's why I wanted to say that to solve this issue, I think I need another criterion, and the other criterion should be not a deviation with respect to the usual solution, but I would like here to put another criterion because here I just pay the price of being, I just changed my estimator of being fair. But maybe from an economic point of view, I should add a price that forces me, that enforce fairness, that could tell me if I'm not fair enough, then I pay a price. And this, for me, should be a relevant criterion. That means if I were looking at something here that tells me you
cannot see the top line. This is blocked somehow for me. I cannot see the headline.
Sorry. Okay, here you see.
No, it's not full screen mode, so therefore I don't see what you see or what the presentation is meant to be.
Okay.
So
now it's full screen.
Now
it's full
screen. Thank you.
Well,
this is my hard constraint I was thinking of. Thank you. So this is now a hard constraint. This means that we have a constraint problem.
Yes.
The convex constraint in addition to the least square procedure.
Yes, exactly. And my main guess, I would like to add another constraint that enforce me to have a minimal amount of fairness. So here I have something here.
Guarantee of fairness. You guarantee a certain amount of fairness in a solution. Okay. Thank you.
And I will and I think a good trade-off will be also to add something the other way around. Let's say I pay some price for not being fair. Here I want to be fair, but I would like another constraint that will tell me if you are not fair, then you you pay some price just to balance. Otherwise, I know the lower bound for being fair, and then I say I put myself at the border of my convex set, my fair set. I put myself at the border and I say, okay, it's enough.
Thank you.
Another question, maybe? Or comments?
Okay, so I think there are no more questions. Yeah. Okay, so thank you, Jean-Michel, again for this very interesting presentation. And to the audience, thank you very much for the interesting questions, and see you next week with another seminar. Jean-Michel, hope to see you in person.